Welcome to the deep dive. We've got a highly technical and honestly high-stakes agenda today.
We really do.
Yeah, we're focusing squarely on the most rigorous chemical and hazard communication concepts that you're going to encounter on the CHST exam.
Right, the Construction Health and Safety Technician certification.
Exactly.
Yeah.
And for anyone preparing for that exam, or frankly, just anyone out there managing a complex job site, mastering this stuff, industrial hygiene, hazard communication, it's completely non-negotiable.
No, absolutely non-negotiable.
We're looking at a framework that governs the invisible hazards on a site. You know, the airborne particulates, the volatile organic compounds that just absorb right through your skin.
The chronic exposures.
Right, the stuff that doesn't show its damage until decades after a project is finished. And to guide us, we've pulled together a massive stack of sources. We're looking at CHST study guides, official GHS pictogram manuals, and some really detailed transcripts from safety expert John Newquist covering all the nuts and bolts of this.
And I think it's important to frame this right out of the gate. The term industrial hygiene often misleads people who are new to the field.
Oh, for sure. They hear hygiene and they think
sanitation,
That's
right?
right.
Keeping the site clean, managing the porta potties, making sure the break areas are wiped down.
just sweeping up.
Exactly.
Yeah.
But in the context of occupational health, industrial hygiene is the science of anticipating, recognizing, evaluating, and controlling environmental stressors.
Stressors that actually make people sick.
Right, things that cause sickness, impaired health, or just significant discomfort among workers. We are talking about literal life and death mechanisms of chemical exposure here.
Yeah.
And the regulations we're about to cover, they weren't just, drafted in a vacuum.
No, they're written in blood.
They are the direct result of historical occupational tragedies.
Yeah, I mean, you look back at the early 20th century, and the total absence of these regulations is just horrifying.
It really is.
Like, take the Radium Dial Company in Ottawa, Illinois. This was about 100 years ago. They manufactured these glow-in-the-dark instruments for aircraft and watch dials using this proprietary radium paint.
And they employed mostly young women to do the detail work.
Right, these young women doing this fine, detailed painting. And to maintain a sharp point on their paintbrushes, these workers were actually instructed to use their lips to shape the bristles.
Just putting radium directly into their mouths.
Daily. They were ingesting radium every single day. And at the time, there was no hazard communication standard. There was no right to know legislation at all.
None.
So these women had no concept of the radiological hazard they were putting into their bodies. And that systemic failure resulted in the radium depositing into their bones. It led to necrosis of the jaw, fatal cancer. It's just horrific stuff.
And the really sad part is that lack of a framework, it persisted for decades after that.
Yeah.
Even much later, you look at the manufacturing of the pesticide DBCP.
Yeah.
Researchers had actually established in laboratory settings that DBCP caused severe testicular atrophy in rats.
The data was right there.
The data existed, yet the chemical operators synthesizing this pesticide in the manufacturing plants, they were never informed of that specific toxicological data.
So they're just walking in blind.
Working in standard clothing. And the chemical was readily absorbing through their dermal layer, through their skin. A significant portion of that workforce suffered permanent sterility. They literally lost the ability to have children because the data existed in a lab, but the communication pipeline to the worker did not exist.
Which is just a massive institutional failure.
And that is the fundamental purpose of the hazard communication standard and the exposure limits we operate under today. It's about bridging that gap between the toxicological science and the actual worker on the floor.
And we are going to navigate that entire pipeline today for you. We're going to start by examining the regulatory bodies that dictate these exposure limits.
Specifically, the friction between OSHA and the ACGIH.
Yes, the legal mandates versus the scientific recommendations. Then we're going to break down the mathematics of time-weighted averages.
Which is a guaranteed competency test on the CHST. You have to know the math.
You cannot escape the math. Then we pivot from sampling the air to sampling the worker. We'll explore biological exposure indices.
BEIs.
Right. Then we'll decode the functional application of the 9 GHS pictograms, clarify the super strict regulatory realities of secondary container labeling, and finally, we'll dissect the architecture of the safety data sheet.
Focusing heavily on Section 8.
Oh yeah. Section 8 is the holy grail, so it's a comprehensive framework. And understanding how these individual components interlock is what separates just rote memorization from actual field competency. So let's just dive right into the regulatory landscape.
Let's do it.
When a worker is exposed to a volatile, solvent, or heavy metal dust, someone has to define the threshold of acceptable risk. If you're reviewing health and safety plans, you are just bombarded with alphabet soup.
Acronyms everywhere. PEL, TLV, REL.
Exactly. So what's the critical distinction for the exam and really for legal liability? Let's start with OSHA and the PEL, the permissible exposure limit.
So the permissible exposure limit is the baseline. It is the federal law.
The law.
Yes. If an industrial hygiene survey demonstrates that your workers are exposed to a chemical at a concentration exceeding the PEL, you are in direct violation of the Occupational Safety and Health Act.
Period.
Period. You are subject to citations, financial penalties, mandatory abatement. It's a legally enforceable line in the sand.
Okay, but if it's the federal law, and complying with the law shields a company from baseline regulatory liability, why would any construction firm voluntarily look beyond the PEL? I mean, I constantly see safety professionals pushing companies to adhere to the ACGIH TLVs, those threshold limit values.
Right.
If a company is under the legal limit, why spend the capital to engineer the exposure down even further to meet a voluntary standard?
Well, you just hit on the primary vulnerability of the entire OSHA system.
Yeah.
The reality is that legally compliant and biologically safe are often two entirely different things.
Elaborate on that.
So when OSHA was established back in 1971, they needed to rapidly implement safety standards across all American industries. They didn't have time to study everything from scratch.
So what did they do?
They largely grandfathered in the existing 1968 standards from the Walsh-Healy Public Contracts Act.
Wait, so the standards are from 1968?
Yes. And the critical issue is that for hundreds of industrial chemicals, those PELs have never been updated since then.
That's wild. Science has changed a bit since the 60s.
Just a little bit. But the rulemaking process for a federal agency is agonizingly slow. It requires exhaustive economic feasibility studies, massive public comment periods, and immense political capital. So you have legally enforceable exposure limits that are based on the toxicological understanding of 1968.
Which naturally introduces the American Conference of Governmental Industrial Hygienists, the ACGIH.
Exactly.
And despite having the word governmental right there in their title, they are actually a private scientific organization. They are not a regulatory agency.
Correct. And because they're a private, non-regulatory body, they are constrained by all those bureaucratic and economic feasibility hurdles that paralyze OSHA.
They just look at the science.
They look at the latest epidemiological data, peer-reviewed toxicological studies, and they publish their threshold limit values, their TLVs, annually.
Every year?
Every single year. A TLV represents the level of exposure that the ACGIH believes nearly all workers can be exposed to day after day without adverse health effects.
So because they're working with modern data, I'm assuming TLVs are generally much more protective.
Almost universally. The allowable concentration for a TLV is almost always lower than the outdated OSHA PEL.
Okay, so we have a legal limit stuck in the past and a scientific recommendation operating in the present. This brings up a really fascinating enforcement dynamic that you have to know for the exam.
The general duty clause.
Right. Let's say a company is operating between those two numbers. They are below the legal OSHA PL, but they are above the recommended ACGIH TLV. Are they entirely safe from OSHA citations?
Not at all. And this is highly testable. Consider the Fiberdome case in Wisconsin. Our sources highlight this because it perfectly illustrates this exact legal friction.
Break down the Fiberdome case for us.
So Fiberdome was manufacturing composite materials, specifically fiberglass components, and they were using adhesives that contained styrene.
Styrene is a highly volatile, toxic solvent.
Very toxic. The official OSHA PL for styrene is 100 parts per million. During an industrial hygiene evaluation, the air monitoring data revealed that the workers at Fiberdome were exposed to an average concentration of 75 parts per million.
Okay, so let's pause there. From a strict compliance standpoint, regarding that specific styrene standard, they were operating legally, right? They were 25 parts per million under the federal limit.
Legally compliant under the specific standard, yes. But the modern ACGIH TLV for styrene, the concentration recognized by modern science as the actual safe threshold, was only 50 parts per million.
Oh, wow.
Yeah. So because these workers were exposed to 75 parts per million, they were actively experiencing acute adverse health effects. The styrene vapor was causing significant upper respiratory irritation, neurological impairment, and actual chemical burns to the workforce.
So the employer points to the 100 ppm limit and says, hey, we're in compliance. Meanwhile, the workforce is actively deteriorating. How does OSHA bridge that gap?
Under the leadership of Dr. David Michaels at the time, OSHA bypassed the outdated specific standard entirely and utilized Section 5A1 of the OSH Act,
The General Duty Clause.
the General Duty Clause. That clause basically dictates that an employer must provide a workplace free from recognized hazards that are causing or are likely to cause death or serious physical harm.
And since the ACGIH TLV was 50, the hazard was recognized.
Exactly.
Good.
OSHA argued that the TLV established the hazard as recognized by the industry and the scientific community. Furthermore, the workers were experiencing documented physical harm. So, despite being under the PEL, the company was cited for failing to protect their workers from a known danger.
And Fiberdome ultimately settled that case.
They did, and it established a vital precedent. You cannot use an outdated law as a shield when modern science and actual worker injuries prove your site is dangerous.
That is such a critical mechanism to understand for the CHST. The PEL is the law, the TLV is the science, but the General Duty Clause gives OSHA the teeth to enforce the science when the law fails.
Exactly.
Briefly, before we move into the actual mathematics of exposure, we should clarify a couple other terms you'll see. RELs and action levels.
Sure. So REL stands for a recommended exposure limit. These are developed by NIOST, the National Institute for Occupational Safety and Health, which actually operates under the CDC.
So NOSH is the research arm, and OSHA is the enforcement arm.
Right. And like TLVs, RELs are scientifically driven recommendations.
Got it. And what about action levels? I see those all the time with high-hazard substances.
Action levels are your early warning triggers. If you're reviewing a standard for a really nasty substance like lead, hexavalent chromium, or crystalline silica, you will invariably see an action level, and it is typically set at exactly 50% of the PEL.
Half the legal limit.
Exactly. The philosophy is that you don't wait until a worker is bordering on an illegal exposure to begin mitigating the risk. When your air sampling indicates you've crossed the action level, it triggers mandatory programs.
Like what?
You have to initiate periodic air monitoring, establish a medical surveillance program to track worker health, implement specialized training, and draft a written exposure control plan. It essentially forces the employer into a proactive posture long before that legal maximum is breached.
Okay, that sets our regulatory foundation. We know who defines the limits. Now we have to translate those limits into actionable data on the site, and that means math.
The dreaded TWA math.
Time-weighted averages. For the exam, you have to be intimately familiar with the three primary categories of threshold limit values published by the ACGIH. Let's start with the big one, the TLV-TWA.
The TLV-TWA is the absolute workhorse of industrial hygiene metrics. It represents the time-weighted average concentration for a conventional 8-hour workday and a 40-hour workweek.
The typical shift.
Right. The toxicological premise here is that nearly all workers may be repeatedly exposed to this concentration, day after day, for a working lifetime, without suffering adverse chronic health effects.
We're going to break down the specific math for that 8-hour TWA in a second, but there are exposures that spike, right? You might have a process that only takes a few minutes but generates a massive cloud of solvent vapor.
Yes, and that is governed by the second category, the TLV STEL, the short-term exposure limit.
STEL.
The STEL is designed to protect workers against acute effects, immediate severe eye or respiratory irritation, rapid central nervous system depression, irreversible tissue damage.
Okay.
A STEL is defined as 15-minute time-weighted average exposure.
Just 15 minutes.
And it is crucial to understand that even if a worker's overall 8-hour TWA is well below the allowable limit, if they exceed the STEL for even a 15-minute window, the employer is out of compliance.
And the rules governing STELs are highly rigid. It's not just a free pass to endure a heavy dose of a chemical whenever you want. There are 3 specific constraints applied to a STEL that you need to memorize.
What are they?
First, the exposure can never exceed 15 minutes. Second, these 15-minute spikes can occur no more than 4 times per typical workday. And third, there must be a minimum of 60 minutes between each STEL exposure.
That 60-minute gap is biologically mandatory. It's rooted in pharmacokinetics.
How so?
When a worker inhales a high concentration of a solvent, their body has to metabolize and excrete that toxin. If they're hit with a second high-dose exposure 20 minutes later, their metabolic pathways are still completely saturated from the first exposure.
They haven't cleared the system yet?
Right, so the toxin accumulates rapidly, and that leads to acute poisoning. That 60-minute interval ensures the body has sufficient time to clear the chemical load before the next exposure cycle begins.
That makes perfect sense. Okay, the third category is the TLVC, the ceiling limit.
The ceiling is the absolute maximum concentration that must never be exceeded during any part of the working exposure.
A hard stop.
It doesn't matter if it's for an 8-hour shift or a 10-second burst. You typically see ceiling limits applied to highly reactive, corrosive, or immediate-acting asphyxiants. Things like hydrogen chloride gas or hydrogen cyanide, where a momentary breach causes instantaneous biological damage.
Okay, so with those three categories defined, the focal point for any safety technician is calculating that standard 8-hour TWA. Because industrial hygiene sampling pumps, they don't usually run for a perfect 8 hours at a constant concentration.
Never. A worker moves through different tasks, using different chemicals, moving into different ventilation zones.
Right, so you have to synthesize those varying exposures into a single standardized number to compare against the PEL or TLV. The formula for calculating a TWA is straightforward, but the application is where people stumble on the exam.
Oh, they fall for the traps all the time.
Let's lay it out. The formula is TWA equals the sum of each concentration multiplied by its respective time duration, all divided by 8.
So C1 times T1 plus C2 times T2 and so forth.
Exactly. Divided by 8. Let's look at that denominator first because that is the trap. Why is the division always by 8?
Because the PELs and the TLV TWAs are standardized against an 8-hour biological clearance model. The toxicology assumes a worker is exposed for 8 hours and then has 16 hours away from the chemical to metabolize and excrete it before the next shift.
So if the exam question states a worker worked a 10-hour shift or a 12-hour turnaround,
Candidates naturally assume they should divide the total exposure by 10 or 12. You must never do that when comparing against a standard 8-hour limit.
why not?
Because if you divide by 10, you artificially lower the average concentration. That might incorrectly indicate compliance when the worker is actually severely overexposed.
Now, I know there are specialized pharmacokinetic models, like the Brief and Scala model that Safety Pros use to adjust the actual exposure limits for extended shifts, essentially lowering the allowable PEL to account for the reduced recovery time.
Right. But for the standard TWA calculation questions you will encounter on this exam, unless specifically instructed otherwise, the denominator remains 8.
Always divide by 8. Let's run a calculation.
Okay.
A worker is performing a degreasing operation. They are exposed to a solvent concentration of 50 parts per million for 4 hours. Then they switch tasks and are exposed to 30 parts per million for the next 4 hours.
Okay, so we apply the formula sequentially. The first exposure period is 50 ppm multiplied by 4 hours. That yields an exposure dose of 200.
50 times 4 is 200. Got it.
The second period is 30 ppm multiplied by 4 hours. That yields 120. Then we sum those doses. 200 plus 120 equals 320.
And finally, we apply our standard denominator.
Exactly. 320 divided by 8 hours results in a calculated time-weighted average of 40 parts per million. You would then take that 40 ppm result and compare it against the chemical's specific PEL or TLV to see if you're compliant.
All right, let's increase the complexity with what our sources refer to as the toluene trap. This mirrors the specific phrasing you'll see on exam questions.
I love this one.
Here is the scenario. A worker is exposed to toluene vapor. For the first 3 hours of the shift, the concentration is 40 ppm. For the next 4 hours, the concentration drops to 25 ppm. And for the final 1 hour of the shift, they are in a well-ventilated area with an exposure of just 10 ppm.
Okay.
The established TLV TWA for toluene is 20 ppm. The question asks, is this employer in compliance?
All right, the chronological breakdown is essential here. Period 1. 40 ppm multiplied by 3 hours equals 120.
Right.
Period 2. 25 ppm multiplied by 4 hours equals 100.
Yep.
Period 3. 10 ppm multiplied by 1 hour equals 10. So we sum up those exposure doses. 120 plus 100 plus 10 gives us a total of 230.
And then we divide by 8.
Always. 230 divided by 8 yields a TWA of 28.75 ppm.
Okay, so we have our calculated exposure, 28.75. We check it against the standard. The TLV is 20 ppm.
So the exposure of 28.75 ppm exceeds the allowable limit of 20 ppm.
You fail.
The employer's out of compliance. They have to implement engineering controls, like local exhaust ventilation or administrative controls to reduce that exposure. Or, as a last resort, implement a respiratory protection program. Mastering that sequence, multiplication, summation, and dividing by 8 is just non-negotiable for anyone operating in this field.
That covers the assessment of the air the worker is breathing. We attach a sampling pump to their lapel, pull the air through a filter cassette, and a laboratory tells us what was in their breathing zone. But the air is really only half of the exposure equation.
It really is.
Because if a worker is wearing a half-mask respirator, the air sample on their lapel might show a massive overexposure. But if the respirator is functioning perfectly, their actual internal exposure is zero.
Exactly. And conversely, the air might be perfectly clean, but if the worker is washing their hands in a bucket of methyl ethyl ketone without gloves.
They're absorbing the chemical directly into their bloodstream systemically.
Right. So to determine what is actually inside the worker, we transition to biological exposure indices, or BEIs.
Air monitoring predicts exposure, but biological monitoring proves it.
That's a great way to put it. BEIs are guidance values published by the ACGIH for assessing biological monitoring results. They represent the concentration of a chemical or its metabolic breakdown products found in biological specimens collected from a healthy worker who has been exposed to the chemical precisely at the TLV TWA concentration.
So we are moving from the lapel to the laboratory. We are testing venous blood, urine, or exhaled breath to map the pharmacokinetics of the exposure. And the nuances of which chemical requires which type of biological sample are heavily tested concepts.
Very heavily tested.
Let's begin with the most heavily regulated heavy metal in the construction industry.
Lead. Lead exposure is ubiquitous in construction. You see it primarily during the demolition of structures containing pre-1978 lead-based paint, abrasive blasting, or the welding and cutting of painted steel.
And lead is a systemic poison.
It targets the hematopoietic system, which disrupts the formation of red blood cells. It attacks the nervous system, the kidneys, and the reproductive organs. The specific biological marker used to track lead exposure is the blood lead level, or BLL.
And that's measured in micrograms of lead per deciliter of whole venous blood, right?
Right.
The regulations surrounding the blood lead level, particularly the medical removal thresholds, are notoriously stringent. And they differ between general industry and construction, which is a classic exam trick. What are the specific metrics a safety tech has to memorize here?
Okay. Under the OSHA lead in construction standard, an employee must be temporarily removed from any work involving exposure at or above the action level if their periodic blood test indicates a blood lead level at or above 50 micrograms per deciliter.
50.
50. That is a critical distinction because the threshold for a general industry is slightly lower at 40 micrograms per deciliter.
And the mechanism of this medical removal isn't just, hey, take a few days off and rest up. It triggers a clause known as medical removal protection, or MRP.
Yes.
This is one of the most punitive financial liabilities an employer can face if they fail to control an exposure hazard.
The MRP benefits are absolute. If a worker's blood lead hits 50 micrograms per deciliter on a construction site, the employer must remove them from the hazardous exposure.
Yeah.
But they are legally obligated to maintain the worker's full earnings, seniority, and all other employment rights and benefits for up to 18 months while the worker's body naturally clears the heavy metal.
18 months. You are essentially paying a worker their full wage for a year and a half while they are prohibited from doing the primary job they were hired to do.
Exactly. It's a massive economic incentive for employers to invest in proper ventilation, hygiene facilities, and respiratory protection long before the blood lead levels begin to rise.
Okay, moving beyond heavy metals, the BEI protocols for organic solvents are equally specific. Let's take mercury, for instance.
Mercury exists in multiple forms, but in occupational settings, we're primarily concerned with inorganic mercury vapor. It's a severe neurotoxin. It induces tremors, emotional ability, profound central nervous system degradation.
And unlike lead, which binds heavily to red blood cells.
Right, inorganic mercury is highly water-soluble once it's metabolized, and it is excreted through the kidneys. Therefore, the biological monitoring for inorganic mercury is conducted via urine analysis, looking for the concentration of mercury per gram of creatinine to adjust for urine dilution.
What about toluene? We calculated its air exposure earlier, but its biological monitoring is unique due to its physical properties, right?
Toluene is a widely used aromatic hydrocarbon solvent. It's common in paints, thinners, adhesives, and it's highly volatile. Now, a portion of it is metabolized by the liver into ocresol and excreted in the urine. But a significant percentage of absorbed toluene is simply off-gassed back out through the lungs.
Just breathe right back out.
Exactly. Because of this high volatility, a primary BEI method for toluene involves capturing a sample of the worker's exhaled breath at the end of their shift to measure the concentration of the unmetabolized solvent leaving their respiratory tract.
That's fascinating. Exhaled air for toluene. The final and arguably most critical BEI example we need to cover is benzene.
Benzene is the quintessential occupational hazard. It's classified by the International Agency for Research on Cancer, IARC, as a Group 1 carcinogen.
A known human carcinogen.
More specifically, it is a potent leukomogen. Chronic exposure to benzene vapor causes bone marrow suppression and is definitively linked to the development of acute myelogenous leukemia, AML.
Because it targets the fundamental blood-forming organs, tracking its systemic absorption is an absolute priority in petrochemical and refining environments.
Yes, and because it's a carcinogen, the acceptable threshold is practically microscopic.
How is it biologically tracked?
Benzene is metabolized in the liver, and one of its highly specific minor metabolites is S-phenylmercapturic acid, SPMA. Biological monitoring for benzene relies on testing the worker's end-of-shift urine for SPMA.
And what's the threshold?
The BEI threshold is incredibly low. It's set at just 25 micrograms of SPMA per gram of creatinine. The precision required to detect a metabolite at that microscopic level underscores exactly how dangerous the chemical is.
So matching the hazard to the specific biological test is foundational knowledge for the CHST. Let's recap that real quick.
We do venous blood, mercury to urine, toluene to exhaled breath, and benzene to SPMA in urine.
Perfect. So we've covered the regulatory limits and the quantitative measurements. Now we need to transition to how these hazards are physically communicated on the site to the workers actually handling the materials. We are looking at the visual language of safety, specifically the globally harmonized system and its 9 pictograms.
HAZCOM 2012. Prior to that update to OSHA's Hazard Communication Standard, which aligned U.S. regulations with the UN's Globally Harmonized System, or GHS chemical labeling, was completely chaotic.
It was the Wild West.
It really was. Manufacturers used varying symbols, disparate rating scales, inconsistent terminology. A worker could look at a barrel of solvent from a European supplier and a barrel from a domestic supplier and receive entirely conflicting visual warnings about the exact same chemical.
The GHS alignment standardized all those classification criteria and established a universal visual lexicon.
Yes, and there is a non-negotiable aesthetic rule that applies to all 9 of these GHS pictograms. A manufacturer or employer cannot simply modify the design to suit their branding.
No custom colors.
The visual standardization is absolute. To be a compliant GHS pictogram, it must feature a solid black hazard symbol centered on a stark white background, and it must be framed by a thick red diamond-shaped border.
That red border is key.
It is a mandatory cognitive trigger designed for instant hazard recognition, regardless of language barriers or literacy levels.
We need to decode the functional application of these 9 pictograms. We aren't just memorizing pictures here. We need to understand what seeing these symbols dictates for a site-specific safety plan.
Let's walk through them.
Let's start with the flame pictogram.
The stylized black flame signifies extreme fire hazards. Highly flammable liquids, pyrophorics that ignite spontaneously upon contact with air, self-heating substances, and materials that emit flammable gases when they contact water.
Like what?
Gasoline, acetone, xylene. When you see the flame pictogram on these materials, it dictates immediate isolation from ignition sources, the implementation of grounding and bonding protocols during fluid transfer to prevent static discharge, and strict adherence to flammable storage cabinet regulations.
The second pictogram is visually similar but functionally very distinct. The flame over circle.
Right. This represents oxidizers.
Yep.
It is crucial to separate the flame pictogram from the flame over circle pictogram in your site planning.
Why? What do oxidizers actually do?
Oxidizers, such as compressed oxygen cylinders, concentrated hydrogen peroxide or ammonium nitrate, they are chemicals that readily yield oxygen or other oxidizing gases. They can initiate or drastically accelerate the combustion of other materials, even in the complete absence of ambient air.
So they don't necessarily burn themselves, but they make everything else burn hotter and faster.
Exactly. If an oxidizer is stored adjacent to a flammable liquid and a fire breaks out, the oxidizer will feed the fire with a localized, highly concentrated supply of oxygen. The result is catastrophic intensification. Therefore, seeing this pictogram dictates strict segregation protocols in your storage yards.
Keep them far apart. Next up, the gas cylinder pictogram. It's straightforward visually, but it implies multiple types of hazards.
It denotes gases under pressure, compressed gases, liquefied gases, and dissolved gases like acetylene. The hazard is twofold here. First is the chemical nature of the gas itself, whether it's an asphyxiant like nitrogen or highly flammable.
And the second hazard?
The universal hazard of the cylinder pictogram is physical pressure. A standard oxygen cylinder is pressurized to roughly 2,200 pounds per square inch.
That's basically a bomb.
It's an unguided missile. If that cylinder is knocked over and the valve shears off, the sudden release of that immense kinetic energy turns that heavy steel cylinder into a projectile capable of punching straight through concrete block walls. So this pictogram dictates mandatory securement, chaining the cylinders upright to a structural support, and ensuring valve protection caps are installed when not in use.
Makes sense. Next is the corrosion pictogram, which shows liquid pouring from test tubes onto a metal bar and onto a human hand.
This indicates chemicals that cause irreversible destruction. It signifies severe skin burns, permanent ocular damage leading to blindness, and materials that are corrosive to metals, which can compromise the structural integrity of tanks or scaffolding.
You'll see this on extremes of the pH scale, right?
Right. Strong mineral acids like hydrochloric and sulfuric acid, and strong bases or caustics like sodium hydroxide. And here's a critical operational reality. A 50% solution of sodium hypochlorite, which is just industrial strength bleach, carries this corrosive designation. Yes. And under OSHA regulations, if your workers are handling corrosive materials, you must provide a suitable facility for quick drenching or flushing of the eyes and body within the immediate work area. The ANSI standard specifies that an eye wash station must be reachable within a 10-second unobstructed walk from the corrosive hazard.
10 seconds. That's good to know for the test. Now we get to the toxicity indicators, starting with the skull and crossbones.
The skull and crossbones specifically denotes acute toxicity. This means the chemical is fatal or highly toxic upon a short-term, immediate exposure.
It's a measure of lethality.
Exactly, often quantified by LD50 or LC50 metrics, lethal dose 50%. If a worker ingests, inhales, or absorbs a chemical bearing this pictogram such as cyanide compounds or arsenic, the biological shutdown is rapid, and emergency medical intervention must be immediate.
But acute lethality isn't the only way a chemical kills you. That brings us to the health hazard pictogram. This is the silhouette of a human torso with a starburst pattern radiating from the chest.
I consider the health hazard pictogram the most insidious warning on a job site because it represents chronic, long-term destruction. While the skull and crossbones kills you during the shift, the health hazard pictogram signifies chemicals that kill you 20 or 30 years after you retire.
The silent killers.
It denotes systemic, irreversible damage. Carcinogens that mutate DNA, reproductive toxins that cause severe birth defects, mutagens and substances that cause highly specific target organ toxicity.
Like the benzene we talked about earlier.
Benzene, asbestos, crystalline silica, lead. When you encounter those, this is the pictogram that warns you of the latency period. The damage is entirely invisible at the time of exposure, making strict adherence to respiratory protection and biological monitoring absolutely paramount.
Next, we have the exclamation mark. It seems a bit less severe than the skull or the exploding chest.
It represents significant, but generally non-fatal, health hazards. It's used for skin and eye irritants, chemicals that cause narcotic effects like dizziness or drowsiness, and most importantly, skin and respiratory sensitizers.
Sensitizers. What exactly does that mean operationally?
Sensitization is an immunological response. A worker might handle a chemical like an isocyanate or certain epoxy resins for months with absolutely no issue. But once their immune system becomes sensitized, even a microscopic subsequent exposure will trigger a massive, potentially life-threatening allergic reaction.
Like severe contact dermatitis or occupational asthma.
Exactly. The exclamation mark warns that the material can permanently alter the worker's immune response.
The next one is the environment pictogram, the dead tree and the dead fish. This introduces a major jurisdictional nuance for the exam.
It does. It indicates acute or chronic aquatic toxicity. If this chemical breaches secondary containment and enters the soil or the municipal drainage system, it will cause severe ecological damage.
But there's a catch for OSHA compliance.
The critical exam trap is that while this is an official United Nations GHS pictogram, it is not actively enforced by OSHA.
Wait, really? OSHA doesn't enforce it?
No. OSHA's statutory mandate is strictly limited to the occupational health and safety of the worker within the physical boundaries of the job site. Environmental hazards and disposal regulations fall under the jurisdiction of the Environmental Protection Agency, the EPA, and laws like RCRA.
So manufacturers include it for shipping and APA rules.
Right, but OSHA does not cite employers for its absence on a secondary container label.
Good to know. Finally, the exploding bomb pictogram.
This denotes explosive materials, highly reactive organic peroxides, and self-reactive chemicals that are liable to undergo a strongly exothermic decomposition, even without participation of oxygen.
TNT, dynamite.
Dynamite blasting caps. Operations involving these materials overlap heavily with ATF regulations regarding storage magazines and security.
Okay, so all of those pictograms are printed flawlessly on the massive 55-gallon drums arriving from the chemical manufacturer. But that is rarely how the chemical is actually applied on the site.
Almost never.
A worker decants a highly corrosive solvent from the drum into a smaller 32-ounce plastic spray bottle to clean a specific piece of equipment. That spray bottle is a secondary container. What are the strict realities of hazard communication once that chemical leaves its original packaging?
The transfer of chemicals into secondary containers is one of the most frequently cited violations in hazard communication. You cannot simply decant a toxic solvent into an unmarked bottle or write cleaner on the side with a marker.
OSHA mandates two specific elements, right?
Yes. The employer must ensure every secondary container is clearly labeled with, first, the product identifier, the exact name of the chemical as it appears on the safety data sheet. And second, it must feature words, pictures, or symbols that accurately and comprehensively convey the specific physical and health hazards of that chemical.
This leads to a highly specific compliance issue regarding how those hazards are visually conveyed. Let's say a company wants to be compliant, so they instruct their workers to draw the GHS pictograms on their secondary spray bottles. A workie grabs a black Sharpie and draws the diamond, and then draws the flame symbol inside it to indicate the solvent is flammable. Is that black and white hand-drawn label compliant?
It is entirely non-compliant.
Wow, even though the information is there.
Even then, OSHA actually addressed this exact scenario in a formal letter of interpretation issued on June 20th, 2017. The agency explicitly ruled that if an employer chooses to utilize the GHS pictograms to satisfy the hazard warning requirement on a secondary container, the border of that pictogram must absolutely be read.
So the visual standardization overrides the practicality of a quick hand-drawn label. Why is OSHA so uncompromising on the color of the ink?
Because hazard communication relies heavily on pre-conscious cognitive recognition. In an emergency scenario, a fire breaks out, or a worker is splashed in the face, there's no time to read fine print or interpret a monochromatic sketch.
Your brain just needs to react.
The brain processes color and shape fractions of a second faster than it processes text. The red diamond is the universal cognitive trigger for a chemical hazard. If you allow black borders, you degrade the standardization of the entire system.
So what's the workaround if they don't have printed stickers?
You can draw a red diamond with a red marker and put a black symbol inside it. Or you can utilize pre-printed compliant stickers. But drawing a black diamond with a black marker on a secondary container is a direct regulatory violation. The integrity of the visual language must be maintained across all levels of the job site.
That level of strict standardization is a perfect transition into our final major topic, the architecture of the safety data sheet, the SDS. This is the master document that dictates every aspect of how a chemical is handled, stored, and regulated.
The transition from the old material safety data sheets, the MSDS, to the globally harmonized SDS was a monumental improvement in industrial hygiene.
How bad was the old system?
Under the old MSDS system, manufacturers had significant leeway in how they presented information. You might find the critical first aid instructions on page 1 of a solvents document, but buried on page 12 of a pesticides document.
So in an emergency, you're just flipping pages desperately.
Exactly. The GHS alignment mandated a strict, non-negotiable 16-section format. Every SDS for every chemical produced anywhere in the world now presents its information in the exact same sequential order.
Before we break down the contents of those 16 sections, we really need to address a staggering administrative requirement regarding how long an employer must retain these documents.
The 30-year rule.
Right. If a construction company finishes a project and disposes of all remaining chemical inventory, can they simply throw the corresponding safety data sheets in the shredder?
Absolutely not. And doing so opens the company to catastrophic legal liability. Under OSHA Standard 1910.1020, which governs access to employee exposure and medical records, an employer is legally mandated to retain chemical exposure records, which inherently includes the safety data sheets for a period of 30 years.
30 years. A 30-year retention rule is an immense administrative burden. What is the legal and medical justification for holding on to a piece of paper for 3 decades?
It connects directly back to our discussion of the health hazard pictogram and latency periods.
Silent killers.
Exactly. If a pipe fitter is exposed to asbestos fibers or benzene vapors on your site today, the biological manifestation of that exposure, like mesothelioma or acute myelogenous leukemia, might not develop for 20, 30, or even 40 years.
So they get sick decades later.
If that worker is diagnosed with an occupational cancer 3 decades from now, the subsequent toxic port litigation and medical evaluations require absolute proof of what exact chemical profile the worker was exposed to during that specific project.
And the SDS is that proof.
The SDS serves as a permanent, discoverable medical exposure record. If an employer fails to produce that 30-year-old document during discovery, they are highly vulnerable to massive liability judgments because they cannot definitively prove what the worker was or was not exposed to.
Okay, let's dissect the 16 sections. We'll move efficiently through the preliminary sections to focus heavily on the technical data critical for the exam. Sections 1 through 3 establish the baseline identification.
Section 1 is straightforward identification. The chemical name, the recommended uses, and crucially, the manufacturer's emergency contact information, which must be accessible 24/7.
Section 2.
Section 2 is hazard identification. This is where the required GHS pictograms we just talked about are listed, alongside the hazard statements and the specific signal word. Either danger for severe hazards or warning for less severe hazards.
And Section 3 details the composition and information on ingredients. This includes the specific Chemical Abstract Service, or CAS, registry numbers, right?
Yes. CAS numbers are unique numerical identifiers for every chemical compound, ensuring you aren't confused by varying trade names.
All right, Sections 4 through 6 are dedicated to emergency response.
Section 4 covers first aid measures, categorized by the route of exposure: inhalation, skin contact, eye contact, and ingestion. It details both the immediate acute symptoms and the delayed chronic effects to watch for.
Section 5 addresses firefighting measures.
This is vital because applying the wrong extinguishing agent can cause a secondary disaster. For instance, if you apply a standard water stream to a magnesium fire, the water will react explosively, producing highly flammable hydrogen gas. Section 5 dictates the exact extinguishing media required.
And Section 6 is accidental release measures, outlining the specific spill cleanup procedures, containment protocols, and the emergency PPE required for the response team. Section 7 covers handling and storage, which dictates the segregation protocols we discussed regarding flammables and oxidizers. But then we arrive at Section 8. For anyone taking the CHST exam or anyone drafting a site-specific safety plan, Section 8 is the undisputed core of the document.
Section 8 is titled Exposure Controls and Personal Protection. This is where the theoretical hazard is translated into physical worker protection.
It's where the rubber meets the road.
Exactly. If you need to know the legally enforceable OSHA PEL for the chemical, it is explicitly listed in Section 8. If you need the more protective ACGIH TLV, it is listed in Section 8. It also establishes the hierarchy of controls, dictating the specific engineering controls required, such as minimum local exhaust ventilation rates, before you even consider providing protective equipment.
And when you do reach the point of providing personal protective equipment, Section 8 strips away all the ambiguity. A generic safety plan might just say, workers must wear gloves and a respirator when handling solvent, but wearing gloves is functionally useless advice if you choose the wrong material.
Totally useless, because chemical permeation and degradation rates vary wildly. If a worker plunges a hand wearing a standard latex or nitrile exam glove into a bucket of concentrated methylene chloride, that solvent will permeate the glove material in a matter of seconds.
It just eats right through it.
It dissolves the polymer and traps the caustic chemical directly against the worker's skin, actually accelerating the biological absorption.
So what does Section 8 say?
Section 8 will explicitly state the required polymer. It will say something like, utilize heavy-duty butyl rubber gloves with a minimum thickness of 15 mils.
The same precision applies to respiratory protection in Section 8, doesn't it?
Absolutely. It dictates the necessary assigned protection factor, or APF. Based on the volatility and concentration of the chemical, Section 8 will specify whether a half-mask respirator with an APF of 10 is sufficient, or if the hazard requires a full facepiece respirator with an APF of 50, or even a supplied air system with an APF of 1,000. It completely removes the guesswork for the PPE selection process.
Moving through the deep science, Sections 9, 10, and 11 detail the physical and toxicological properties.
Section 9 provides the physical and chemical properties, boiling points, vapor pressure, and specific gravity. Specific gravity is huge because it tells you if the vapor is heavier than air and will sink into trenches in confined spaces.
Section 10 is stability and reactivity.
Right, highlighting specific conditions to avoid, like static discharge or extreme ambient heat, to prevent hazardous polymerization or decomposition.
And Section 11 is the deep toxicological information.
Providing the numerical toxicity data, like the LD50s we discussed, and confirming if the substance is recognized as a carcinogen by the National Toxicology Program, or IARC.
Then we hit sections 12 through 15. There is a massive jurisdictional trap here for the exam. And SDS has 16 mandatory sections globally, but OSHA only legally enforces sections 1 through 11 and section 16. What is housed in 12 through 15 that puts them outside of OSHA's purview?
It comes right back to statutory jurisdiction. Section 12 is ecological information, how the chemical bioaccumulates in the environment. Section 13 covers disposal considerations. Section 14 is transport information, detailing the UN shipping numbers and placard requirements. And Section 15 is general regulatory information regarding other national and international safety, health, and environmental regulations.
And OSHA doesn't enforce those.
OSHA's mandate ends at the property line of the job site. The environment, the landfill disposal, and the highway transportation are the sovereign jurisdictions of the EPA, the Department of Transportation, the DOT, and international maritime bodies.
So they have to be on the sheet, but OSHA won't cite you for them.
Therefore, while a manufacturer must include these sections to maintain a compliant 16-section document, an OSHA compliance officer will not issue citations based on the contents of sections 12 through 15.
And finally, section 16 is other information, which predominantly tracks the document's revision history. It's a critical administrative check to ensure you are referencing the most currently updated toxicological data and not some obsolete sheet from a decade ago.
That completes the 16-section architecture. It is a highly rational, interlocking system designed to guarantee that from the moment a chemical leaves a manufacturing facility to the moment it is applied on your site, the hazard profile is universally understood.
Well, we have navigated an immense amount of technical terrain today.
We really have.
We define the regulatory friction between the legally enforceable OSHA PELs and the scientifically rigorous ACGIH TLVs, noting how the general duty clause can override an outdated law. We broke down the mechanics of the 8-hour time-weighted average calculation, divide by 8.
Always divide by 8.
We explored biological exposure indices, matching lead to blood, mercury to urine, toluene to exhaled breath, and the highly carcinogenic benzene to microscopic traces of SPMA. We decoded the critical applications of the 9 GHS pictograms, including the uncompromising mandate for red borders on secondary container labels, and we dissected the anatomy of the safety data sheet, focusing on the 30-year retention liability and the life-saving engineering and PPE specifications housed within Section 8.
It is an incredibly robust, meticulously engineered system of communication and protection. But it leaves us with a critical ongoing vulnerability.
What's that?
We built this massive infrastructure to track, measure, and mitigate hazards based on existing toxicological data. We know exactly how to manage benzene today because we spent decades observing its devastating leukomogenic effects on previous generations of workers.
The ones who suffered before the rules were in place.
Right. But the global chemical industry is continuously synthesizing thousands of novel compounds, complex polymers, and engineered nanoparticles every single year. These materials are entering the supply chain and arriving on job sites at a staggering pace.
And the epidemiological studies required to definitively prove that a novel chemical causes chronic target organ toxicity or cancer can take decades of observation to yield statistically significant data.
Exactly. There is an inherent unavoidable lag between chemical innovation and safety regulation. So the question that every safety professional must grapple with is this: how do we manage the unknown?
That's the real challenge.
When a completely novel, poorly understood compound enters your job site tomorrow morning, a compound with no established PEL, no historical TLV, and an incomplete toxicological profile in its SDS, are we truly capable of protecting the workforce? Or, despite all of this sophisticated regulation, are today's workers still acting as the biological guinea pigs, slowly generating the tragic data that will eventually be used to write the exposure limits of the next generation?
Wow. That is the reality of the front lines of industrial hygiene. The regulations provide a baseline, but the responsibility to anticipate and aggressively manage the unknown falls entirely on the safety technician and the employer. Thank you for joining us on this exhaustive deep dive into hazard communication. We hope this arms you with the technical depth required to not just pass the CHST exam, but to aggressively protect the people relying on your expertise out in the field. Stay rigorous, stay vigilant, and stay safe.